So we've been having great fun solving oblique triangles using the law of sines. But you'll notice that we're kind of limited with the law of sines in that we can't solve oblique triangles if we're not given the right information. For example, let's suppose we were just given the lengths of the three sides of a triangle but no angles. In other words, let's suppose we have a side, side, side situation. Well, we can't use the law of sines to solve that. Or let's suppose we have a side and another side and its included angle between the two sides. Well, we can't use the law of sines to solve that triangle either. So what's called for is the law of cosines. And what we want to do today is develop the law of cosines, and I want to show you an example of how you use the law of cosines. Now, we'll start off by, I'm going to use the coordinate system here where you have the horizontal axis and the vertical, the xy coordinate system. And I drew an oblique triangle such that this side down here on the axis goes from 0, 0 to C0. So this side is length C. And then, of course, you have xy up here. That's the point, the vertex here for angle C. And then, of course, angle A and angle B and side B and side A are labeled. Now, this is an oblique triangle. And what I want to do as I develop this law of cosines, I want to calculate the distance from this xy point here, this arbitrary xy, down to this C0. So I'm going to calculate the distance. And of course we use the distance formula, which is the sum of the squares of the coordinates, the difference of the squared differences. So I have the difference of the x's squared plus the difference of the y squared. Take the square root of that and I'll have this distance. So we're going to use the distance formula, and I want to now square both sides. So I've got a equals the square root of this. If I square both sides, I now have the radical eliminated, and I just have a squared equals this. Now, I want to make a substitution in here for x and a substitution for y. And here's how I'm going to proceed. I'm going to observe that cosine A is the adjacent over hypotenuse, so x over b. And then I multiply both sides by b, and I have x equals b cosine A. So I'll put that in place of x. And for y, I'll consider sine A, where I have opposite over hypotenuse, which is y over b. Multiply both sides by b, and I get b sine A for y. So I'll replace the y with b sine A. And now just do the multiplication. And notice squaring this first one, I get this. And then squaring b sine A, I get b squared sine squared A. Now, I want to simplify this, and I'm going to proceed this way. Recognizing that I have cosine squared here and sine squared here, and I know that if I put those together I get 1. Sine squared A plus cosine squared A equals 1. So I'll do a little bit of a rearranging, just moving this b squared sine squared A over here with cosine, and then I'll factor out the b. You notice each one of these has a b squared, so I'll factor it out. And then just make the substitution that that's equal to 1. Cosine squared A plus sine squared A equals 1. And now we have this. A squared equals b squared plus c squared minus 2bc cosine A. This is the first part of our law of cosines. Now, it's not the only part, but it's the part that I'm going to derive for you, and then by a similar process you can get the other parts. Now, here's what we have. This is what I've just derived, this first part. Now, all I did, this is excellent for finding out what A is. So you have a squared equals b squared plus c squared minus 2bc cosine a. Now let's suppose you want to find out what angle A is. Well, you would use this part. And the way I got this part was simply by solving this equation for cosine A. I subtracted the b squared and the c squared and then divided by negative 2bc. Also, we have b squared equals a squared plus c squared minus 2ac cosine b. And similarly, I found the formula for finding the angle b. Now notice this. The similarities here. Notice if we're a squared is equal the sum of the squares of the other two sides minus 2 times the product of the other two sides times the cosine of the opposite angle. So that's one way you can remember it. So here we have b squared, so what's left? A and c. So it's a squared plus c squared minus 2ac cosine b. And likewise, c squared equals a squared plus b squared minus 2ab cosine c. Okay, so there's a lot of similarities here. And then, of course, I have the cosine c for occasions when we need to find the angle c. Now let's look at an example. Let's suppose we're given this information. Now, of course, this is an example of side, 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 where the law of sines is not going to help us right away. So we have to use the law of cosines. Now, here's the thing you want to remember with using the law of cosines. Oftentimes, when you begin using the law of cosines to solve a problem, for example, we're trying to solve this triangle, you're going to want to transition over to using the law of sines because many people find the law of sines easier to use. Now, for that reason, when you start off using the law of cosines, what we want to do is we want to find an angle. The reason we can't use the law of sines now is because we don't have an angle. We don't have the right information. So we need an angle. Now here's what you do. Use the law of cosines to find the largest angle first. That's a good practice to be in because sometimes it's going to benefit you a great deal. So now remember, the angle that's the largest is going to correspond to the angle opposite the longer side. Well, in this case, that would be angle B. So we want to find angle B. Now here's why. If you find an angle that's not the largest, and let's suppose you find an angle that is an acute angle, you have set yourself up to encounter the ambiguous case when you transition over to use the law of sines. Now it's nice to be able to transition over and use the law of sines, but oftentimes what will happen is if you find the acute angle, you will have a situation like, for example, if we find angle A, we'll have an angle side side, which is the ambiguous case, and it's possible that we can encounter that we now have two possible solutions. So we don't want to do that. We want to find the obtuse angle, and remember, for a triangle to have two solutions, you have to have the angle that you're given to be acute. That's a necessary condition. So if we find an obtuse angle, we know that we can proceed and there's not two solutions. So I'm going to find angle B. So I put in the A squared, the C squared, and the B. Then down in the bottom, 2AC, make that computation, and I get negative 0.45089. Take the inverse cosine, and I have that B is 116.8 degrees. Now, we have an angle, and we have all the information we need to use the law of sines. So let's do that. Let's transfer over to the law of sines. Now remember, because we found this angle to be obtuse, we can go ahead now and use the law of sines. We don't have to worry about the ambiguous case. So now we come over here and we implement the law of sines. We have sine A over 8 equals sine 116.8 over 19. Solving that, we get A is approximately 22.08 degrees. And then, of course, C is 180 minus the sum of the previous two angles, A and B. And we get that C is 41.12 degrees. So here we have it. Angle A is approximately 22.08. Angle B is approximately 116.8. And angle C approximately 41.12.